Hey guys, Mr. Smith here, and in this video lesson, we're going to be talking about an application of logarithms in the sciences. Specifically, we're talking about logarithmic scales. So I'm in the dungeon again. I think for the time being, this might be my preferred recording spot. So we'll just make the best of it. Now, you may, depending on like some of you guys have already taken some chemistry, so you probably have some experience working with logarithmic scales. But even if you haven't taken chemistry, log scales show up in everyday life, and you've probably heard of the Richter scale for earthquakes, possibly the decibel scale for sound intensity. Um, um, but yeah, as a motivation problem, one logarithmic scale we're going to look at is the pH scale, and the pH scale basically tells you how acidic or alkaline something is. And the how acidic or alkaline something is, it depends on the amount of hydronium ions in a substance. And for for I won't say like common everyday items, but things that like we're not talking about like space materials, like so for for blood, orange juice, some acids you might have in a chemistry lab, the range of hydronium atoms in moles per liter can vary widely over a huge range of values, many powers of 10, orders of magnitude. So, with the example here, is that some very alkaline things, not very acidic, might only have 1 times 10 to the minus 15 moles per liter of hydronium, whereas something very acidic might have zero point 0.1 moles per liter. That spans about 14 orders of 10. And to give you guys an idea of that, if I just head to Desmos and if I wanted to kind of like maybe plot those on the same graph, so might use, well, 14 orders of 10. So maybe I'll do it this way to show you how challenging it can be. If I wanted to say graph like 100 and 10 million on the same graph, I can't even do it in Desmos. It's actually even just too big. So let me just maybe start over again with this. I think I have an idea that'll work. I'm going to plot a point, I don't know, 110. Oh, there we go, 110. And I'll plot the point 2, 1, and 3, 0.01. So that's only spanning 2 orders of magnitude from 10 to 0.1. If I do 0.001 for 4, and then 5, 0.0001. I mean, as you can see, the difference is imperceptible. It's near impossible to compare in the graph and to think about the differences here when the orders of magnitude differ by so much. And so, in order to be able to make comparisons and do sketches to compare values, we use logarithmic scales. And we're going to do 3 examples today with 3 different logarithmic scales. You've probably heard about all 3 of these, on different levels. So the first one we're going to look at is the pH scale. If you haven't taken chemistry or not taking chemistry, don't worry. pH is just a way to measure how acidic something is or how basic something is, the alkalinity. The equation that defines pH is right here. So don't worry about all the variables floating around. The pH is just, it's not P times H, that's just pH level. And it's dimensionless, has no units. To get pH level, you take the negative of the log of the concentration of hydronium atoms. And on the pH scale, typically you guys see a pH of 1 to pH of 14. But those 1 to 14 actually spans 13 different, or 13 powers of 10. So to just get a bit more understanding about that, let's just dive in and do a few simple questions. So tomato juice has a hydronium ion concentration of about 0.0001 moles of hydronium per liter. Let's turn this into a pH. What's the pH level of tomato juice? So let's find that out. To do that, we're just going to use our equation. pH equals negative log of H plus. And yeah, we have to get our calculators handy. I think I'll do A and B on the front side of our document here. So for A, pH is equal to, so our formula is the negative of the log of the number of hydronium ions. And here we have that's just equal to 0.0030. And now you guys can just use this on your calculators. We don't need to write the 0.0001 as a base of 10. We have experience now using our calculators for evaluating logs. So you guys can just slam in the log of 0.0001. I know it's -4 because that's 1/10,000th, but you can just plug in log 0.0001, get -4. The negative of -4, 4. So tomato juice has a pH level of 4. So fairly acidic. Let's try another one. Blood has about 4 times 10 to the -7 moles per liter for a hydronium concentration. Let's see if blood is acidic or alkaline. So acidic will be less than 7 on the pH scale, and then alkaline or basic will be more than 7. So let's find out. Use the same process. pH equals negative log of H plus. Okay, in this case, 4 times 10 to the -7. And now this won't give us a nice round number like the log of 0.001. So we'll need to use your calculators. And this is scientific notation. On my calculator, my scientific notation button is an EXP button. So I'll do 4 EXP -7. So I can show you guys. So I'm doing the log 4 EXP -7. So my scientific notation button, looking backwards here, is this is so hard to do. This is so hard to do. EXP button is right for me. It's right above my 7 EXP. This allows me to do scientific notation. So I did the log, and then I did the log of 4 EXP -7, and you can see on my calculator it shows up as 4 times 10 to the -7. And when I do this, I got about -6.4. So the pH level of blood, about 6.4. So blood is slightly acidic. We found that by finding its pH level. Let's turn this equation on its head. So orange juice has a pH of about 3, so it's pretty acidic. Let's find the concentration of hydronium atoms in orange juice. So to do that, we're going to take, and what we're going to do, we're going to take our pH equation. Now, what we could just do is plug in the value for, plug in the pH and solve for H plus. That would be just fine. But in case you guys do more of these questions later, let's rearrange this equation for H plus right now. So that if you're doing some textbook work later, you don't have to keep rearranging. So yeah, let's isolate H plus. So let's get rid of the negative sign. Let's move it to the left. So an equivalent form would be negative pH equals the log of H plus. And we can turn this into an equation. H plus is the result, 10 is the base, an exponential equation, 10 is the base because we're using the common log, and then the exponents would be negative pH. So we've rearranged this formula to get a formula for H plus, and now we can just use it. So 10, so if the pH is 3, the number of hydronium atoms, the concentration in moles per liter, would just be 10 to the power of minus 3, 0.001 moles per liter would be the concentration there. Yeah, the nice thing now is that you guys could just use this rearranged formula like moving forward when you guys are doing practice. Let's have a look at tomato juice and orange juice. So for tomato juice, or for orange juice, we had orange juice, we had 0.001, just making sure I get the bigger one on top. And tomato juice had 0.001. If you divide these two numbers, you get 10. And what this shows you is that orange juice has a concentration of hydronium ions, I'll just say of H plus, 10 times higher. Tomato juice had a pH of 3. I might just show this on here. So tomato juice had a pH of 4, This was tomato juice. pH was 4. And then orange juice, the pH was equal to 3. So you'll notice one jump in pH level corresponded to a 10 times jump, one order of magnitude in the concentration of hydronium ions. So this is why these logarithmic scales are so useful. So from a pH of 1 to 14, which would be it would be very manageable to graph that range of pHs on a graph and actually see the differences. That range in pH scale can cover a very wide range of values, 13 orders of magnitude. And we just kind of showed why. One pH level corresponds to a jump in 10 times higher. All right, so we just talked about this. So the ratio of hydronium ions in orange juice compared to tomato juice was 10 times as high. Let's just summarize what we did. It was 10 times as high. And the key idea that we just talked about, a pH difference of -1 corresponds to a 10-fold increase in hydronium ion concentration. Every time you drop down on the pH scale, the acidity is going up. The amount of hydronium per mole is going up by a factor of 10. Okay, so that's the pH scale. Played around with that, did a variety of questions with that. Another scale used in the sciences is for sound intensity, the decibel. The decibel scale we're going to look at in a second allows you to compare how intense one sound is over another. And in the pH scale, an increase of 1 in pH level corresponded to a factor of 10 increase. On the decibel scale, an increase of 10 decimals represents a 10-fold increase in sound intensity. And so I've just lifted the diagram from the McGraw-Hill Ryerson textbook. So what you just to talk about this, so you have obviously very loud sounds up near the top that can damage your ears or possibly kill you, and then you get to sounds that are barely perceptible or hardly audible, like a rustle of leaves. Now, if you compare the rustle of leaves to a whisper, that's an increase of 20, an increase of 10 two times. What that means is, so for a rustle of leaves, you have some loudness. A decibel level of 20, which is 10 more, would mean that sound would be 10 times as loud. Because a whisper is an increase of 10 two times, that corresponds to 10 times 10. A whisper is 100 times as loud as a rustle of leaves. And from whisper to normal conversation, that's 3 jumps of 10. So on the decibel scale, that's 10 times 10 times 10. A normal conversation is 1,000 times as intense as a whisper. An equation that models how the difference in sound levels allows you to compare two sound levels and their intensity is given here. So here, beta 1 and beta 2, they're the sound levels in decimals. So beta 2 minus beta 1 is the difference in those. And I2 over I1 is a ratio of sound intensities. So let's actually just kind of put into practice what we just talked about. So for A, we're going to look at how many times as intense as a whisper is the sound of a normal conversation. So we just kind of roughly talked through this, but let's see how the equation works. Got lots of space here. Lots of space here. So for A, so we're given beta 1 is a whisper, 30 decibels. Beta 2, normal conversation, 60 decibels. And what we're looking for is the ratio I2 over I1. That's what we're looking for. So if it's equal to 10, it's 10 times as intense. If that ratio is 100, 20 times as intense. If it's 50, 50 times as intense. So we can use our equation. So I'll just write it out here. So beta 2 minus beta 1 equals 10 times the log of I2 over I1. Again, the 10 is there because on the decibel scale, unlike the pH scale, an increase of 10 corresponds to a factor of 10. Whereas with the pH scale, an increase of 1 on the pH scale corresponds to an increase by a factor of 10. So let's plug in our stuff. 60 minus 30 equals 10 times the log of I2 over I1. We'll just do one step at a time here. Got lots of space. 10 times log I2 over I1. And dividing both sides by 10, we get 3 is equal to the log of I2 over I1. All right, now we can rewrite this in exponential form. The base is 10 because it's common log. The exponent is 3, and that gives us the result I2 over I1. And so we're done. I2 divided by I1 is equal to 1,000. 1,000 times as intense. So we'll just write that down. A normal conversation is 1,000 times as intense as a whisper. So pretty cool. Another thing we can do with this is to solve for one of the sound levels. So normal city traffic, about 85 decibels. So not harmful to the ear, but it's pretty loud. Riding a snowmobile, a lot louder, 32 times as intense. Let's find the sound level when riding a snowmobile. It's not on our thing here. Let's see if it's in the pain threshold. Should we be wearing protective equipment? Let's find out. So for part B, we're given beta 1, 85 decibels. And we're given the ratio I2 over I1, 32 times as intense. And what we're looking for here is beta 2. So let's just plug in our stuff and solve for beta 2. So beta 2, I'll write out my formula, equals 10 log I2 over I1. Plug in our stuff. Beta 1 is 85. 10 times the log I2 over I1 is equal to 32. I'm just going to get beta 2 by itself right now. So I'll just bring the 85 over. 85 plus 10 times the log of 32. And log 32 is going to be a decimal value, which is okay. So we're going to get an approximate value here. Again, that's okay. And your calculator can just handle that all at once. 85 plus 10 log 32. 85 plus 10 log 32. So I got pretty near 100 when I plugged that in. So roughly 100 decibels. I've been naughty and not including my units for these guys. Decibels, decibels, decibels. There we go. So that's pretty interesting. So it's only a jump in 15 decibels, but corresponds to a 32 times jump in the sound intensity. The decibel level of a snowmobile is 100, about 100 decibels. Okay, cool. So another example of a logarithmic scale in real life, sound intensity. The third one we're going to look at, and I'm sure you guys have heard of this one, is the Richter scale. So earthquakes, kind of like pH levels, have a huge variety in their intensity. So you can have like very small, imperceptible earthquakes, or really huge, building shaking earthquakes. And in order to, in order to compare them, we have to use the logarithmic scale. And this equation is pretty straightforward. We say the magnitude of the earthquake. So when you hear like, oh, a 7.3 magnitude earthquake or a 6.4, this is given by a logarithm of the intensity of the earthquake you're looking at divided by a standard intensity of a low level earthquake. What's the standard intensity of a low level earthquake? Not quite sure. It's pretty low level, probably imperceptible to humans. But if you guys get into earth sciences, that's something you might consider. But let's look at a measuring of 2.4 on the Richter scale. How many times is intense that compared to that standard earthquake, that standard low-level earthquake, would that be? So for part A here, we're given the magnitude and we're finding that ratio. So for A, we're given the magnitude is 2.4, and we're looking for that ratio of intensity divided by the standard intensity. So let's just use our equation. So you notice this one is kind of like the formula for the pH scale, because unlike decibels, an increase in one level on the Richter scale is a factor of 10 increase, just like the pH level. So that's why they both have similar looking equations. And let's plug in what we know. So 2.4 equals log I over IO. Okay, and to get this, we can just rewrite this in exponential form. So this is a base of 10 because it's common logarithm. The exponent is 2.4, and this is equal to the result I divided by I naught. And then we'll just use our calculators to finish this off. I over I naught equals whatever 10 to the power of 2.4 is. But 251. So 251 times as intense. What's crazy to think about with this scale is that, if you see, on TV or on YouTube, like earthquake videos where people can see their rooms are shaking, they can see their buildings swaying a little bit. Those might be like 5 or 6 on the Richter scale. And then we've had earthquakes that are magnitude of 8. And if you go from a magnitude of 5 to a magnitude of 8, that's 1, 2, 3 levels on the Richter scale. That's 10 to the power of 3 times as intense. So those massive earthquakes, those biggest earthquakes in history, are like 1,000 times as big as the earthquakes that are actually visibly like shaking things off shelves and stuff. It's quite crazy to think about. So let's look at what the magnitude of an earthquake 1,000 times as intense as a standard earthquake. So this is just playing around with the Richter scale formula. In this case, you're given the ratio. Okay, what if it's 1,000 times as big? What is this? What does this measure on the Richter scale? Well, let's find out. So we'll plug in 1,000, log of 1,000. And log of 1,000, you guys can probably do with mental math. 10 to what power is 1,000? Or use your calculators. But this is equal to 3. This would be 3 on the Richter scale. So those are the three scales that you guys should get comfortable working with. It is possible that as a bit of an extension, we could introduce, like I know in your text practice, there's a logarithmic scale regarding stellar luminosity, I think, called the stellar scale. But these are the three that you should get comfortable using. Make sure you do the practice. Would be fair game for our unit test. To wrap up, remember the reason why we use these logarithmic scales is because it gives us a way that we can compare. Remember on Desmos, 10 to 0.0001, that's only 5. That's 1, 2, 3. That's 4 orders of magnitude difference. And you can already see it's impossible to compare them on a graph. So we use these logarithmic scales, and they can help us compare over a very big range. We looked at 3 phenomena in sciences. We looked at the pH scale, and we looked at the sound intensity. We also looked at the Richter scale. So get comfortable, do the practice, guys. Get comfortable with these 3 scales. And hope you guys enjoyed that lesson. I enjoyed giving it. Hope you guys are staying well. Take care, and we'll see you soon.